Today we're going to talk about what happens when we change the angle of an incline. So I have the stapler sitting on this incline right here. And here's the force diagram of the forces that are acting on the stapler. Weight always goes straight down towards the center of the earth, as we've talked about. The normal force, by definition, always goes perpendicular up from a surface. And since this thing is on an angle and wants to go down the incline, friction's job is to oppose that desire, so it goes up the incline. We've talked about the idea that we can only deal with forces that are either parallel or perpendicular to a surface, in which case weight gets knocked out. It's not parallel or perpendicular to the surface. We've got to change that. How do we change that? We change that by breaking weight into its components. So these two things right here are the components of that weight force. These are the actual forces. If this was a AP question or a test question, that you would have to put this diagram on here. However, it's easier to deal with and work with that picture because everything is either parallel or perpendicular to the surface. So if you look at this thing, since this thing is in equilibrium, then the sum of the forces parallel to the incline is 0. And the sum of the forces perpendicular to the incline is also 0. So, the short way for us to say that is that Fn is equal to W perpendicular, and Ff is equal to W parallel. And it's pretty easy to see how that might be the case. Now, there is a coefficient of friction. So this is the amount of friction, but there's also a coefficient of friction that's describing these two surfaces in contact. The wood board and the bottom of the stapler are two surfaces in contact. And that coefficient of friction is called, as we know, mu. And in this case, it's a static coefficient, which has a maximum value. So let's talk a little bit about that maximum value of the static coefficient. Well, the coefficient of friction is friction force divided by the normal force. So if we take the ratio of the friction force to the normal force, that's what the coefficient of friction is. Well, we've already talked about here how friction force is equal to the parallel component of the weight, and the normal force is equal to the perpendicular component of the weight. So I can make this equal to W parallel, and this is equal to W perpendicular. Well, what is W parallel? Well, W parallel is W sine theta, and W perpendicular is W cosine theta. So look at what happens when I plug that in. That's W sine theta divided by W cosine theta. Well, most people, when you say the trig, get a little bit frightened, right? But basically, what do we know? What is these two W's go away, and what's sine over cosine? That's the tangent of theta. So our static coefficient in these inclined situations ultimately reduces to the tangent of theta. Now, that seems a little bit weird, right? Because as I change the angle, the tangent of theta is increasing, right? So theta is increasing, and that actually increases the tangent of theta if you know your trig functions. Either way, what that's saying is that this static coefficient is changing. Well, that's weird since it describes the two surfaces in contact, yes, right? Which is really the real reason why the main thing we use this coefficient of static friction for is for its maximum value. It's odd that static friction coefficient can change because it describes the two surfaces and the surfaces aren't changing. It's just a mathematical anomaly. We actually talked a little bit about it a few days ago. But so as I increase this, I keep increasing. The theta keeps going up, so the tangent of theta keeps going up. So our static coefficient keeps going up because it actually takes more force to keep this thing stationary. So we keep increasing this. Now my angle is getting bigger. The tangent of my angle gets bigger. My coefficient gets bigger. Oh, And then ultimately, this thing begins to slide down this way at this particular angle. Well, if it begins to slide down, then we no longer have a static coefficient. So there was some angle here where the thing is not moving, and then I raise it and all of a sudden it moves. There's that one particular angle, that maximum angle of theta, where we end up with our maximum value of the coefficient of friction. So if we think about this thing, right, I can get this all the way up to this particular angle before that thing begins to slide down. If instead of putting the stapler on there, I put the physics textbook on there, you can see that I can't get it to the same angle. The reason I can't get it to the same angle is because there's different surfaces. So our maximum coefficient of static friction between the book and the incline is different than the maximum static coefficient between the stapler and the incline. Now let's talk about what happens when we increase this angle, or decrease. But in this case, we're operating at a low angle, and let's see what happens when we increase that angle. So here's my angle theta between the incline and the ground. Now, look at what happens if I increase that angle, right? So here's theta 1, and let's call this, now you know what, let's just make it theta, right? And let's make this angle alpha, right? So if theta is less than alpha, look at what happens. Over on this side, then so our W parallel is W times the sine of theta, right? And our W perpendicular is W times the cosine of theta. Well, what happens when I have an angle that is bigger than a different angle? Well, if this angle goes up, then the sine of 0 is 0, and the sine of 90 is 1. So as my angle goes up from 0 to 90, or any place in that range, the sine of the angle actually gets bigger as well. So over here, we have a bigger parallel component of the weight, right? So what's the significance of this happening? W parallel is getting bigger. That's what's happening. Well, the cosine of the angle goes from 1, the cosine of 0 is 1, and the cosine of 90 is 0. So this angle is actually causing, this change in angle is actually causing the cosine to become smaller, right? So W times the cosine of alpha is less than W times the cosine of theta. What's that mean? As I increase the angle, the perpendicular component of my weight is getting smaller, right? So what did I just say? So as I do this, let's put the stapler back on there. As I do this, right, there's a component of the weight going down. There's a component of the weight going perpendicularly upwards. As I increase the angle, the component of the weight that's pushing this thing down the incline is getting bigger. And the component of the weight that's sticking it to the surface is getting smaller. All right, well, what's the significance of that? Well, first off, if this thing is getting bigger, if W parallel is increasing, right? So if W parallel is getting bigger, there's more of a tendency for this thing to be sliding down the incline. So there's more of a tendency to slide down the incline. All right, well, what happens here? If Fn gets smaller, right, or if W perpendicular gets smaller, as this thing gets bigger, W perpendicular is getting smaller. Well, what's W perpendicular equal? It equals the normal force. So if W perpendicular is getting smaller, therefore my normal force is getting smaller. Well, if my normal force is getting smaller, then guess what? The friction force is equal to mu times the normal force. So if my normal force gets smaller, then my friction force is going to get smaller as well. And what's that mean? So we got two things happening here. Right now, I've got a component of the weight that's pushing down and friction that's resisting and pushing back up. Well, as I increase this angle, the portion of the weight that's pushing down is getting bigger, 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 bigger. What else is happening is that the amount of resistance to pushing down is getting smaller. So my friction force tends to get smaller. So we have less resistance to going down the incline. Now, of course, the maximum or the greatest example of this, if I took my stapler like this and I kept increasing, again, the portion of my weight that's pulling this thing down is getting bigger. The portion of my weight that's sticking it to the surface gets getting smaller. If I put the surface like this, like weight always acts down. So now all of the weight is going down the incline. There is no portion of the weight that's going perpendicular to the incline because weight never acts in this particular direction. So right here, my W perpendicular is 0. Therefore, my normal force is 0, and therefore my friction force is 0, which is in part why things just slide down the incline like that.